Argus AS-014 pulsejet. The Argus AS-014 was a jet engine with almost none of the machinery normally associated with jet engines. It had no compressor, no turbine, and no rotating core. Instead, air entered through a grid of spring-loaded valves at the front. Fuel was injected and ignited. The pressure forced the valves shut, and the expanding gases escaped through the long exhaust tube. As the pressure dropped, the valves opened again, and the cycle repeated dozens of times every second. The result was the violently pulsing sound that gave Germany's V-1 flying bomb its distinctive mechanical buzz. The first successful Argus pulse jets produced roughly 660 pounds of thrust, later increased to around 770 pounds. They were crude, inexpensive, and simple enough for mass production. The engine did not even need to operate continuously in the smooth manner of a conventional turbojet. It propelled the V-1 through thousands of separate explosions arranged into rapid succession. Its simplicity came with consequences. The engine was noisy, inefficient, intensely hot, and dependent on sufficient forward airflow. Early V-1s were launched from ramps using a steam-powered catapult because the pulsejet could not simply accelerate the heavily loaded weapon from an ordinary runway. The AS-014 used not elegant propulsion. It was an exhaust pipe that repeatedly contained an explosion just long enough to point it toward Britain. Caproni-Campini motorjet. The Caproni-Campini N.1 appeared to be a jet aircraft, sounded like a jet aircraft, and was initially celebrated as one of the first jet aircraft ever flown. Its engine, however, contained a piston engine. Italian engineer Secondo Campini did not use a gas turbine to drive the compressor. Instead, a conventional Isotta-Fraschini piston engine turned a ducted compressor inside the fuselage. Compressed air moved into a combustion chamber, where additional fuel could be burned before the gases escaped through an adjustable exhaust nozzle. The arrangement became known as a motor jet. It allowed Italy to produce jet-like thrust without mastering the extremely difficult turbine technology being developed elsewhere. But it also forced the aircraft to carry the weight and complexity of both a piston engine and a jet duct. The N.1 first flew in 1940 and completed a publicized journey from Milan to Rome in 1941. For a brief period, Italian reports presented it as evidence that the country had entered the jet age. In reality, the aircraft was slower than many contemporary propeller fighters. Its piston engine consumed power merely to compress air, while the burning fuel produced too little additional thrust to justify the arrangement. The motorjet was not a shortcut to the future. It was a conventional engine working extremely hard to impersonate something that would soon make it obsolete. Rolls-Royce RB.162. The Rolls-Royce RB.162 was designed to perform only one part of flight. It was built as a lightweight lift engine for vertical takeoff aircraft. Installed upright inside a fuselage, it would produce thrust directly downward, help lift the aircraft from the ground, and then become almost useless once forward flight began. That specialization shaped the entire engine. It had to generate as much thrust as possible while adding very little weight. Rolls-Royce used simplified construction and incorporated glass fiber reinforced materials in components where conventional engines normally depended heavily on metal. Experimental aircraft could carry several RB.162s purely for vertical lift, combined with separate engines for normal flight. The proposed German VAK-191B, French Mirage Ensive IV, and other projects explored variations of this arrangement, but every lift engine became dead weight after takeoff. It occupied internal space, consumed fuel during the most demanding phase of flight, and still required the aircraft to carry another propulsion system to move forward. The engine eventually found an unexpected operational role aboard the Hawker Siddeley Trident 3B airliner. Installed in the tail, a single RB.162 provided approximately 5,250 pounds of extra thrust during takeoff, helping an aircraft that had become heavier than its original engines comfortably allowed. It was a vertical lift engine that achieved regular service by becoming an airliner's emergency fourth engine. Rolls-Royce Pegasus. Most jet engines point backward. The Rolls-Royce Pegasus could point downward as well. Developed for the aircraft that became the Harrier, the Pegasus used 4 rotating exhaust nozzles positioned along the sides of the engine. 2 discharged cooler bypass air from the front section, while 2 handled the hotter exhaust from the core. For conventional flight, all 4 nozzles pointed rearward. For vertical takeoff, they rotated downward together. At intermediate angles, the pilot could use vectored thrust for short takeoffs, slow flight, unusual maneuvers, or transitions between hovering and forward movement. This eliminated the need for separate lift engines. The same engine that raised the aircraft vertically also accelerated it through normal flight, but the solution placed extraordinary demands on the engine and pilot. The four nozzles had to move together, the aircraft's balance had to remain under control, and hot exhaust could be drawn back toward the intake while hovering near the ground. Vertical takeoffs also consumed fuel rapidly and limited the payload the aircraft could carry. Despite these complications, the Pegasus succeeded where many competing systems remained experimental. It powered operational Harriers for decades and allowed combat aircraft to operate from small carriers, temporary pads, roads, and damaged airfields. The Pegasus was strange not because it performed an engineering trick, but because that trick became reliable enough for ordinary military use. Fairey Rotodyne Tipjet System. The Fairey Rotodyne's rotor was not driven by a normal mechanical transmission. It was driven by small jet engines at the blade tips. The Rotodyne was intended to combine a helicopter's vertical takeoff with the speed and range of an airplane. For takeoff and landing, compressed air was sent through passages inside each rotor blade. Fuel was added near the tips and burned inside small combustion chambers, creating thrust that spun the rotor without requiring a heavy gearbox to transfer full engine power through the aircraft. Once airborne, conventional propellers pulled the Rotodyne forward. Airflow kept the large rotor turning through auto-rotation, allowing it to behave more like the wing of a gyroplane. The system worked. The prototype first flew in 1957 and later reached speeds approaching 175 knots, far faster than many contemporary helicopters. Unfortunately, each rotor tip jet passed repeatedly through the air above the same area, producing an intense pounding noise. The sound became a major obstacle to the Rotodyne's intended role carrying passengers between city centers. Noise reduction trials showed progress, but development costs increased while potential airline orders disappeared. The program was canceled in 1962. The Rotodyne proved that a rotor could be spun by burning fuel at its outermost edges. It also proved that placing several small jet engines above a city was easier than persuading anyone beneath them to accept the noise. Pratt & Whitney J-58. The J-58 powering the SR-71 Blackbird behaved differently depending on how fast it was already moving. At lower speeds, it operated largely as an afterburning turbojet. Air entered the compressor, mixed with fuel, passed through the turbine, and entered the afterburner. Beyond approximately Mach 2, 6 large bypass tubes redirected part of the compressed airflow around the engine's hottest core and delivered it farther back toward the afterburner. The propulsion system gradually began behaving more like a turbo ramjet. At the SR-71's cruise speed of approximately Mach 3.2, the engine alone was only one part of the process. The movable inlet spike positioned shock waves to slow and compress incoming air, while the inlet, bypass system, engine, afterburner, and ejector nozzle operated as one enormous integrated machine. NASA analysis found that during high-speed flight, the inlet and exhaust system generated more than 80% of the total propulsive force, while the engine core contributed less than 20%. This meant the Blackbird's apparent engine extended far beyond the metal cylinder carrying the J-58 name. Parts of the aircraft's nacelle that looked like housing were actively producing most of the force that kept it moving. The J-58 was a turbojet that became increasingly successful by allowing more of the air to avoid being processed like ordinary turbojet air at all. General Electric GE36 Unducted Fan. The GE36 looked as though someone had removed the casing from a turbofan and forgotten to put it back. Developed during the 1980s, it belonged to a class of engines known as prop fans, or unducted fans. The objective was to combine the fuel efficiency of a turboprop with the speed of a modern jet airliner. Instead of hiding a large fan inside a circular nacelle, the GE36 placed 2 rows of enormous swept blades outside the engine. The rows rotated in opposite directions, recovering energy from each other's airflow and producing thrust without the weight and drag of a conventional fan duct. Its mechanical arrangement was even stranger. A modified F404 gas generator core powered a multi-stage counter-rotating turbine connected directly to the 2-blade rows. This eliminated the large reduction gearbox normally needed to turn propeller blades at suitable speeds. The engine was successfully ground-tested and flown on modified Boeing 727 and McDonnell Douglas MD-80 aircraft. Smithsonian records credit it with reducing fuel consumption by approximately 32% during flight testing, but fuel prices declined before the engine reached commercial service. Airlines were also concerned about cabin noise, vibration, maintenance, and the appearance of exposed high-speed blades beside the fuselage. The GE-36 worked. The economic emergency that justified accepting its complications did not remain long enough to make airlines want it. It was a jet engine stripped of the part that made passengers comfortable standing near one, the structure surrounding the fan.